As we begin our discussion of Chapter 8, we want to remember where we have been in previous chapters. We've talked about reactions, chemical changes, and physical changes. What we're going to focus on in this chapter is that aqueous reaction, the AQ state, not a solid, liquid, or gas, but the AQ. And what does it mean? What we want to tie that to is the idea of a solution. So, a couple of definitions to start off, we'll be able to look at qualifying a solution, what is necessary for it to be classified as a solution, and then also quantification, looking at how do we express this homogeneous mixture in terms of numbers and units. So solution concentration and solution stoichiometry. What we just have done in the previous chapter was stoichiometry based off of grams to grams conversions through the mole ratio of a balanced equation. Now, when we have a solution, it's a homogeneous mixture. And so, therefore, we don't often weigh out in mass. We don't usually have that value. What we do have is a volume. And so, when we look at solution stoichiometry, we're going to see that different units are able to be utilized in stoichiometry. Namely, instead of grams, we'll be able to use the milliliter or liters, volume type units. So what is a solution? Well, the best example that we can think of that probably all of you have seen before is when table salt, sodium chloride, is mixed with water. We've done this when we have boiled pasta. First thing that comes into my brain, you put some salt in the water. What that does is it not only flavors your pasta, but it will allow the water to boil at a higher temperature. We'll see colligative properties in the second semester of general chemistry. Right now, we want to be able to say what happens when we throw salt into water. Now, it seems to disappear or become a liquid, but in reality, what's actually happening is that the mixture is becoming homogeneous. The salt is still there, and you can tell it from tasting it. Or if you boil all the water away, the salt will still be there. And so what actually happens is that homogeneous mixture is two components. It's the minor component, not the less important. Minor meaning usually a smaller amount. And that is called the solute. This is something that usually is dealt with in a reaction. It's the component that usually comes into reactivity. For our saltwater example, it would be the sodium chloride. Now, the solute is usually what we write when we're focusing on a solution. This solute is going to be the most important amount, but we call it the minor component because it's the smallest value usually. The major component, or the component that is usually in a higher amount, is called the solvent. This for us will be water. Now, water, not that water is unimportant or doesn't react, but when we look at these two components, typically the reaction component, the component that's undergoing some sort of physical or chemical change, will be the solute. The solvent, water, is going to stay and hang out as water. So when we are looking at a solution concentration, there's a couple of different categories that we want to be able to look at when we're trying to come up with these quantitative values. Now, the word dilute solution is usually gearing us to a small amount of solute compared to solvent. We can think dilute as being a very small value for the concentration. A concentrated solution is our terminology for something that may be a large amount of solute compared to solvent. With concentrated solutions, we usually call those stock solutions in the lab. They're usually high values, things that are almost pure in terms of the solute. Now, whenever we are debating between concentration, what we're going to be able to use is a molarity. Molarity is going to be our number one way of quantifying the concentration of a solution. Now, this image, I like this image from your textbook because it's defining how we actually prepare a solution. So your solute usually goes into your volumetric flask first. A volumetric flask is utilized because it tells you the volume of the solution, which will be very important when we see the units of molarity. Now, the solute can be a solid, a liquid, or a gas, right? Some solids with water, salts, sodium chloride, we could think potassium bromide, that's another thing that could be added. Liquids, acetone, the nail polish remover that we use, you can get at any CVS or any pharmaceutical store. That is, acetone is a liquid. It does mix with water and it makes a more dilute solution. It's not 100% acetone like you get at Home Depot. That is a paint stripper, but it's a maybe 5 to 10% solution that can remove nail polish. Liquid to liquids, right? Gases in water are also very common. We think of soda. How do we get carbonated beverages? We bubble carbon dioxide into that water and we pressurize it so that the gas stays in the liquid solution. So a solute doesn't have to just be a salt. It can be anything. We will focus primarily on salts at the beginning of this chapter. We'll move into acids and bases towards the end. Gases we will hold for second semester general chemistry. So we won't see a lot of gases as solutes, but I just wanted to make sure that we know they're there, they're real life, they exist. With the water, after you add the solute, then you can add the solvent. That water is the solvent, and you add water until the solid is dissolved. You usually shake it up at that point, and then there's usually a little mark on the side of the container on this volumetric flask. And if you haven't been in a lab to see one, I'll show you one in class so that we are well aware of what it looks like. But that mark tells you a specific volume for the total solution. It's a volume mark. Usually it's a whole number, something like 1 liter. It could be 500 milliliters. It could be 25 milliliters. They're very specific to the solution preparation. And so what we see here is that the identity of molarity is very important. How we will quantify a concentration is by taking the moles of the solute and dividing it by liters of solution. Notice that that denominator is of the total volume of solution. Why this is important to note is because notice that that volume mark right there is of the entire component, the solute and the solvent. So we're not, in making this solution, just adding a specific volume of water. We have to take into consideration that the solute has volume too. And the solvent has volume as well. That liters of solution in the molarity calculation is both the volume of the solute and the volume of the solvent. So when you make a solution in the laboratory, it's very important to be able to use a volumetric flask so that you know you're adding enough water to reach the total volume of the solution at your desired volume, which in this case, in the picture, is 1 liter. If you add 1 liter of water, you're going to be over 1 liter of water for the total volume of solution, because you have to be able to quantify the solute volume as well. So molarity. Molarity is the amount of solute in moles divided by the volume of the solution. Remember, total volume. This will be very, very important for us to work with because this will be our way of being able to find out, instead of using a molar mass, we can use the molarity to find out the moles in a given amount. For instance, where before we used a molar mass to convert from grams to moles, now in a solution, when we know that what's better is a volume, we can convert using molarity from liters to moles or moles to liters. So for example, a 0.500 molar sodium chloride solution contains 0.5 moles of NaCl for every 1 liter of solution. If you weigh out, let's say, 15 milliliters of solution, you can find out how many moles are in that sample. What we would want to do is take that 15 milliliters, convert it into liters using our prefix multipliers. You still need to know these. Those will not be given to you. And then we can use molarity to find just the moles of NaCl. Please again, make sure that your units are canceling appropriately. And we're left with 0.0075 moles of NaCl in that 15 milliliter sample. So again, unit conversions, just using now a new type of starting material, a volume. So, okay, let's just look at this one more time. If we wanted a 1 molar solution and we wanted it to have a final volume of 1 liter, that's where we're adding in the 1.00 moles of NaCl, add enough water to reach the 1 liter, 1.00 moles of solute, sodium chloride, divided by 1 liters of solution gets us our 1.00 molar NaCl solution. So what we'll practice with is starting with specific grams of solute or even milliliters of solute and converting using molarity between volume, moles, and grams. Why I like to even take it back through grams is because grams are relatively familiar to us. So I want to still bridge the gap between Chapter 7 and Chapter 8. Now, there is a way to make a new solution from an already prepared stock solution. What this means is that you want to make a dilute solution from a concentrated one. So one solution has a high value concentration and you're trying to make something that's smaller. Now what we would want to use is not necessarily our molarity values or finding the moles, dividing it by liters. What we can use is the dilution equation. The only time we can use this dilution equation is if we are just adding water to a stock solution to make it less concentrated. So usually, typically, a situation in the lab is you need to make a 1.0 molar HCl solution. How do I know that's a solution without even writing HCl? Is it has a concentration. Again, we are going to be assuming that everything is in water as the solvent. All you have is a 12.0 molar HCl solution. Well, this is a perfect setup for dilution. We have a desire to make something that is low in concentration, dilute, but all we have to make it is not a solid, but a concentrated solution. That's when you would use this equation, M1V1 equals M2V2. The molarity of the first solution and its volume is equal to the molarity of the second solution times its volume. Noticing that all we're doing in dilution is changing the volume of solution, the moles of HCl should not change. So here's the setup. You want to make a 1.0 molar HCl solution at, let's say, 500 milliliters. All you have is a 12.0 molar HCl solution. How many milliliters of the concentrated HCl do you need? In this type of a setup, what's important to note is that our M1, V1 are the volume and molarity that are related to each other. M2 and V2 are the volume related to the second solution. It doesn't matter which solution that you want to put in here, but what is important is that you get which solution has the unknown. We don't know how much concentrated solution we need here. And so what we want to be able to utilize is this idea, 12.0 molar, we don't know how much to use. So V1 is unknown. I know I want a 1.0 molar solution at 500 milliliters. I can be in any volume units as long as I'm consistent. This should look similar to P1 V1 equals P2 V2 for gas laws, and that is a-okay to relate it to. As long as you know that you're consistent, you can come up with the correct value. Now with this, we can solve for V1 as being 42 milliliters, keeping my sig figs at 2. Now that means 42 milliliters of the 12.0 molar HCl solution. The other 458 milliliters will be water. We'll be practicing with this throughout our discussion today and throughout class. Now, here's another example. You have a 0.150 liters of a 10 molar stock solution, and you're adding enough water to reach 3.00 liters. What we see here, why M1V1 works, is that when you multiply M1V1, molarity times volume is moles. And molarity times volume in the diluted solution is the same amount of moles. So when we're looking at this dilution equation, it's never going to be utilized for stoichiometry. It will never be utilized in a reaction. What it will be utilized with is a dilution, when we want to take a concentrated solution and make it into a dilute solution. Notice that even in this example, we have calcium chloride. That doesn't react, that doesn't change. We're just diluting the solution, not reacting it. For solution stoichiometry, we can utilize molarity the same way that we utilize molar mass. In a reaction, if we wanted to be able to convert from amounts of reactants or products to another reactant or product, we can use molarity to convert any type of volume units to moles. So how do we do that? Molarity times volume. Just like we saw in M1V1, molarity times volume will be our gateway to moles. So here's our example. If I have 20 milliliters of a 0.50 molar NaCl solution, how many moles is that? Well, we notice that liters can cancel with liters. We're left with moles in the numerator, and we can do the math and see 0.010 moles of NaCl exist in that solution. So things to consider where we can branch off from what we have seen before. When things react in stoichiometry, and we'll practice this a lot in class, we can start with grams of our reactants or our products, and that uses molar mass. If we have a volume, we must use our molarity for that. Okay. Now, types of aqueous solutions and the idea of solubility. What we want to be able to think about are there two main types of familiar aqueous solutions, solids adding to water. The first one, salt water, sodium chloride dissolves in H2O. And the other one you can think of that you've probably also done before is sugar in water, C12H22O11, sucrose in water. So how do solids such as salt and sugar dissolve in water? It's the primary idea that like dissolves like. When we're looking at something being able to dissolve in water, there has to be some sort of solute-solvent interactions. Yes, we know the solvent interacts with itself and the solute interacts with itself, but there has to be an attractive force between the solvent molecules and the solute particles. So we do know that there are attractive forces holding the solute together, there are attractive forces holding the solvent together, but when we mix, the solute and the solvent must be interacting in a favorable, attractive way. Remember, attractive forces are energy releasing. Exothermic. That was Coulomb's law telling us that if two things are attracted to each other, then energy is lowering, energy released from the system, exothermic. That's favorable. It means that the solution will form for us. If the attractions between the solute and solvent are strong enough, the solution will form. If for some reason these solute-solvent interactions are not favorable, we do not get a solution forming. So think about water. We've talked a lot about the structure of water so far, and we have shown that it does have a dipole moment. It has a polarity. The oxygen is the delta minus, the hydrogens are the delta plus. So we do know there's an uneven distribution of electrons within water. So what this causes is the idea that oxygen has a negatively charged pole, or a partial negative charge pole, and hydrogen has a partial positive charged pole. When we introduce an ionic compound such as sodium chloride, opposites can attract. So the delta minus, I'll make it a little bit bigger, is attracted to the delta plus. These are called ion dipole forces. We will investigate them a lot more in the second semester of general chemistry. But what we can relate now is that opposites attract. Even if one is an ion, an actual negative or an actual positive charge, and the other one is just a polar delta, positive or negative, opposites attract. And that is favorable for the solution to form, because once we bring these components together, they can interact and they can hang out. So dissolving sodium chloride in water, the ions are actually attracted to the surrounding water molecules, and they can pull off away from the actual crystal lattice structure. Remember that lattice, that was the buildup, that was the driving force to form the solid compound, actually can be broken up because of these attractive forces with water. So the result is a solution with free moving charged particles, positives from the sodium, negatives from the chlorine, and they're separated. So technically, they haven't reacted. They've just separated themselves from the crystal lattice. What this allows us to see as a physical property is that solutions of ionic compounds dissolved in water can conduct electricity. Because of those free-flowing ions, we know they have broken up and they're separated from the crystal lattice so they can interact with the water. But that gives us charged particles that we can actually conduct electricity with. So looking at the non-electrolyte versus electrolyte definition. Now, I like bringing this in here because we've probably heard of electrolytes before. You think of Gatorade or any power drink or anything that says, oh, there's electrolytes. All they're saying is that they have ions dissolved. Sodium chloride, potassium bromide, things like that that are dissolved in the liquid base of your solution, your drink, right? So when materials that dissolve in water form a solution that will conduct electricity, that is called an electrolyte. It means that there are ions present. So there must have been a salt that is able to dissolve in that water solution to form the solution. Now, materials that dissolve in water but don't form a solution, or that don't form a solution that conduct electricity, is called a non-electrolyte. Sugar is a very good example of a non-electrolyte solution. It doesn't conduct electricity. And the reason for that is because, yes, it interacts with water, it can dissolve, but there are no ions present. Now, if we look at those two structures, sodium chloride is an ionic bond. C12H22O11, sucrose, is a covalent compound. And so they're covalent bonds. There are no ions present anyway. So on the molecular level, what's happening is the sodium and chlorine actually break apart. And the ions form in the solution. For sucrose, no bond actually breaks. There's no separation of ions because there were no ions to begin with. Yes, we still have solute and solvent interactions because we have delta pluses reacting with or interacting with delta minuses, delta minus, delta plus. There's a delta minus. Remember, colors are important to recognize. The red there is oxygen. Oxygen is usually more electronegative than hydrogen, the white circles. And so therefore we see hydrogens, the white circles, having the delta positives, the oxygens, the red circles, having the delta minuses. So we still have all these dipole interactions, which are favorable. But over here, we have our ion dipole interactions. Again, favorable, but can conduct electricity as well. So when we're looking at this on the molecular level, sucrose is still a holistic unit, right? It hasn't broken apart, unlike the sodium and chlorines that have broken apart, and those actual charged particles can conduct electricity, whereas the sugar water cannot. So, electrolyte solutions. They're classified by the idea that there is a dissociation of the solute into its ions. Now, it has to be completely dissociating into its ions in order to be called a strong electrolyte. So when we form a solution, if we have a strong electrolyte, we will only have products present. The solid is gone. So what we mean by completely dissociate is that the solid completely breaks up its crystal lattice structure. Now there are things that are called weak electrolytes. A weak electrolyte is not going to be seen as an ionic compound. What we'll see is that this will be classified as our weak acids. Our acids, as we'll see here, are molecular compounds. So, strong electrolytes, if a salt dissolves in water, if an ionic compound dissolves in water, it will be assumed as a strong electrolyte. If we have a molecular compound that completely dissolves in water, then we'll see a couple of different examples. They could either be a strong electrolyte or, like in sugar, a non-electrolyte. What we mean by weak electrolyte is that it's a molecular compound that can dissolve in water, but it doesn't often like to. It creates what we call a dynamic equilibrium. Notice those arrows, a half arrow forward and a half arrow back. Now, we won't be discussing or diving into that dynamic equilibrium, but it means that the ions are present, but also the original product or the original reactant is present. The CHOOH is also still there. It doesn't completely ionize or dissociate. And so what we'll start to see once we get further into chapter 8, the weak electrolytes are mainly classified by weak acids, molecular compounds that are not great at dissolving in water. All right, ionic substances such as sodium chloride that completely dissociate, we'll call those strong electrolytes. As a little bit of a hint, hint, wink, wink, where are we headed? When we get into acids and bases, that's where we're going to see we can have strong or weak electrolytes. I want to save that until we get to the strong acids and strong bases and weak acids and weak bases. I want to get through our first topic, which is the ionic substances. And again, what we'll see is that non-electrolytes like molecular compounds of sugar, this is not an acid or base, this is just a molecular compound. And again, we'll be able to define acids and bases soon. But if it's a molecular compound, it does not dissociate into ions at all because no ions are present, then we must call it a non-electrolyte. So, okay, just to see the imagery here, very, very strong electrolytes, such as salts that dissolve in water, make the light bulb very bright. Non-electrolytes, like sucrose, no electricity at all. So, light bulb is not on. We can also have a weak electrolyte, which is kind of working, but not really. Things like weak acids will be our primary focus. And again, we'll focus on them a little bit later in this chapter. So, ionic compounds. When an ionic compound dissolves in water, the resulting solution contains not the intact ionic compound itself. There's no more lattice, but it's a complete component of ions dissolved. But not all ionic compounds actually dissolve in water. AgCl, that's what we see right here, silver 1 chloride. It remains a solid and appears as a white powder at the bottom of the beaker. It is not soluble. It is what we call insoluble, meaning it is not able to dissolve in water. So we'll say no solution here. Soluble is the term that says a solution will form. Sodium chloride is soluble in water. Silver 1 chloride is insoluble in water. If silver nitrate is added to water, it dissolves and forms a strong electrolyte. Look at that, our particulate diagram. What we see is that, it should just be N, typo in the book. What we see is that there's a nitrate ion and silver ions all over the place. The silver chloride is insoluble, and so we still see the lattice at work. No lattice at the top, lattice on the bottom. So what's the big deal? How will we know? Well, that's a great question. Can we predict when a salt will dissolve? Well, there's a couple of factors that we have to take into consideration. Charge, size. The best way to do it is with experiments to test whether a compound will dissolve or not. And then there are some rules that help us. So we're going to stick with the rules because this is a lecture course, not a lab course. But with the rules, table 8.1 are great solubility rules for ionic compounds. Now, let's read this chart together so that we can truly understand what's happening here. Because utilizing this chart for studying purposes is very important. when we see compounds that contain group 1 cations, lithium, sodium, and potassium, along with ammonia, NH4 plus 1, these compounds are always soluble. There are no exceptions. So when we see on that column on the left, it says compounds containing the following ions are generally soluble. Because lithium, sodium, potassium, and ammonium do not have any exceptions, we call them always soluble. What does that mean? Well, potassium iodide, it has potassium, always going to be able to be a strong electrolyte. Something like NH4Cl, always able to form a solution, always a strong electrolyte. Whenever we see one of these 4 ions, notice they're +1 charges, relatively small. Whenever we see these, we will always assume that they are in an aqueous solution. Next one, nitrate -1 and acetate -1. These polyatomics are also always soluble. There are no exceptions to those. Whenever we see them in a compound, let's say calcium nitrate, always going to be a strong electrolyte. Doesn't matter what it's paired with. If you see nitrate, always soluble. If you see acetate, always soluble. Moving right along, here comes some exceptions. Chloride, bromide, and iodide, Cl-, Br-, and I- are most of the time soluble. They are insoluble when they are paired over here with the resulting cations, silver, mercury, or lead. When we have any of those anions paired with silver, mercury, or lead, the resulting compound is insoluble. So, for example, let's say calcium chloride. Well, chloride and calcium's not one of the exceptions, so aqueous. But let's say lead iodide. Iodide, but it's with an exception. Solid, insoluble, not forming a solution, so therefore solid at the bottom of the beaker. All right, last one of our solubilities, sulfate, usually soluble except when paired with strontium, barium, lead, silver, or calcium. When sulfate is paired with one of those 5 cations, the resulting compound is insoluble. So again, work with it, see what you can see with practice problems. We'll move down to the bottom of this chart. These are the insolubility rules. So how we would read the last 2 rows here is saying hydroxide and sulfide are generally insoluble, except when they're with the group 1 or ammonia cations. Well, that you can't go against rule number 1 way up here, right? I'll number them just so that we can utilize the numbering system. Or sulfide when he pairs with calcium, strontium, or barium. Or hydroxide when he pairs with calcium, strontium, or barium. Those resulting compounds for sulfide are soluble. For hydroxide, they're slightly soluble. We'll count it as soluble. Last one, carbonate and phosphate. These are usually insoluble except when they're paired with group 1, cations or ammonia cation. So when we're looking at these insolubility rules, they are generally more complex. So be careful with them. Look at them as if they're saying any hydroxides, sulfides, carbonates, or phosphates are usually insoluble. The exceptions say when they are soluble. So, why is this important? Why do we even want to know these rules? Well, in a reaction, what's important to understand is that you may mix two aqueous solutions and something starts to fall out of the solution. Something starts to precipitate. If you're not part of the solution, you're part of the precipitate. So this type of a reaction is when you're going to have a solid product form. Now, we classified the types of reactions last time. What we usually see for these precipitation reactions is a double displacement reaction. Also sometimes called double replacement, same idea. We're going to see two ionic solutions, they're aqueous, that are going to be mixed together, and the ions do a do-si-do. The ions are going to swap, and we'll be able to look at those products and see, is there one product that is technically insoluble in water? And that insoluble product is going to be called the precipitate. So when we look here, potassium iodide solution is mixed with lead nitrate solution, lead 2 nitrate. And a yellow lead 2 iodide precipitate forms. What's happening here is the ions are being able to separate and merge together, and when a lead ion reacts with an iodide ion, an insoluble compound forms, and they stick together like two little magnets, and they will form that solid at the bottom of the solution. Now, what I like to be able to visualize here is this idea of the do-si-do. Potassium is a cation. He's going to mix with the anion of the other compound to form potassium nitrate. Potassium is K plus 1, nitrate is NO3 minus 1, so they form KNO3. Iodine, the anion, will form with the cation of the second compound. I minus forms with Pb plus 2 to form PbI2. Then we look at those products and say, well, are they aqueous or are they solid? Are they soluble or not? Well, if I look at rule number 1 or rule number 2 from before, potassium, always soluble. Nitrate, always soluble. So potassium nitrate is going to be aqueous. Now, if I think of lead iodide and go back to my rules, iodide is usually soluble except when he's mixed with lead. Solid, there's my precipitate, which I like to abbreviate PPT. Now, what does this mean for our reaction? Well, if we form an insoluble compound, we will get a reaction to occur. We will make that product and it will fall out of the solution. If we do not have any precipitate forming, we do not have a precipitate reaction forming at all because everything would stay in its ion form. So be very careful when we're starting to identify the do-si-do, okay? KCl, I mixes with Na, so NaI. We would call these both aqueous. Well, then they're ions. Nothing truly happened. Now we just have a sea of ions. So no precipitate, no precipitation reaction. So overall, what's the thought process? What we want to be able to do is determine what ions are in the aqueous solution on the reactant side, right? So determine their charge. That might be inferring, right, by the cross-cancel method, things that we've done before in previous units. And then determine the formulas of the possible products. Do the switch of the ions. Do the do-si-do. The cation of one pairs up with the anion of the other reactant. And make sure that we're balancing the charges of those combined ions to get the right product. Subscripts written on the reactant side tell us the charges of their pair species. So be very careful with this. And then determine the solubility of each in water. Use the solubility rules to determine if a product is soluble, slightly soluble, or if it just is going to be aqueous. Couple more. If neither product will precipitate, write no reaction. Don't write those products, you just write no reaction. But if products are insoluble, at least one, then write all of the formulas that you would have seen. The insoluble product gets the solid state, the soluble products get the AQ state or the aqueous state. Don't forget, at the end of the day, we need to balance the reaction as well. We're going to be able to practice with this in a second. Just want to focus in on these rules. So here's an example, all right? And we're going to try to utilize those rules as much as possible. So if you need to flip back and forth, that would be awesome. If I want to mix potassium iodide and lead 2 nitrate, what am I going to see? Well, when I mix them at first, I'm going to see a whole bunch of ions in the solution, right? There are my ions. They were there when I had the 2 separate components. Now I'm going to mix them. So what I need to do in my very first rule, or my very first step, was determine what ions do I actually have. So I would look at this and start splitting things up. Potassium iodide, K plus 1, I minus 1. Lead, Pb plus 2. How did I know? There's that little subscript. It was a cross charge, right? We use the cross charge rule. Nitrate is the polyatomic, you should still know, NO3 minus 1. There are my ions. Now I need to be able to predict the products. And remember, the anion of one goes with the cation of the other. So 2 cations cannot mix. So I'm going to bring potassium and nitrate together. And then I'm going to bring lead and iodide together. When those form together, Pb plus 2 and I minus 1 becomes PbI2. Lovely. States. Potassium always aqueous, so slap that on there. Nitrate always aqueous. Iodide with lead, solid. So what I see here is that I do indeed have a reaction. And that reaction is going to form products. One of them is solid, so I'm going to get the products to be formed. So when I look at these products, what I want to be able to now say is I've determined their solubility. I've assumed, or I've been able to clarify that there is a reaction. I wrote the states there. Now I need to balance. Well, I have 1 potassium on each side. I have 1 iodide on the reactant side and 2 on the products. So put a 2 in front of potassium iodide. I have 1 lead, 2 nitrates, and 1 nitrate. Put a 2 in front of potassium nitrate. That should balance my equation and be completely neutral. Lovely. Now, in this type of aqueous reaction, we are showing the neutral formula of everything, meaning in that reaction, I have potassium iodide paired up. I have lead nitrate paired up. I have potassium nitrate paired up and lead iodide paired up. I have the neutral forms of the actual formula unit. That's not really what's happening. This is called a molecular equation. It's a great way to see the complete neutral formulas. But as we know, these are ions in solution if they are aqueous. So what we can do is start to think about what dissolved substances are present as ions and write an ionic equation. Now notice in this ionic equation, what we've done is that if something was aqueous, we split it up into its ions. Again, aqueous. We split it up into its ions, making sure that we've still kept the balance. Aqueous, ions. And yet if something is solid, we've kept it solid, right? Be very aware of that magnesium hydroxide, not in ions. No ions here because of the solid precipitate, not part of the solution. So why is this important? Well, it gets to the overall idea of what's actually happening in this reaction. Now, an ionic equation has a couple of rules, and those are the ones we just went through. Aqueous things are strong electrolytes, so they should be written as ions. Soluble salts, strong acids, strong bases. We'll get to those strong acids and strong bases in a little bit. Insoluble substances or weak electrolytes or non-electrolytes, all of these do not like to produce ions. And so when we look at them in the actual ionic equation, they are stuck in their formula unit or their molecular formula. They do not separate. They do not get to dissociate into the ions. Now, what's helpful about these ionic equations is we get to identify things that don't change, that shouldn't technically be written in the equation itself. Notice that in that complete ionic equation, some of the ions appear on both sides, namely nitrate. There were 2 nitrate ions on each side and 2 potassiums. These are what we call spectator ions. Notice how the term spectator, where do we see it before? Well, when you're hanging out at a ball game, right? You're not playing baseball. The baseball players are playing baseball. Spectator ions don't hang out in the reaction or don't do anything in the reaction. They're just hanging out. They're just watching. And so what we actually can do is physically cancel them out and say they do not participate in the reactions. Yes, they're present in the ionic equation, but now we can write a net ionic equation. What is actually happening to produce that solid? Well, the spectators get removed, and all we see is that the 2 ions meet to form the solid insoluble compound at the bottom. The net ionic equation will not have the spectator ions written. When the spectator ions are removed, the chemical reaction is now a little bit more specific, and it's the net ionic equation that is the net reaction, the overall reaction that's actually happening for us. Let's practice one more time. Potassium carbonate and nickel 2 chloride, both aqueous to begin with. Let's predict our products, write the ionic and the net ionic reactions, and see the differences. Again, we'll always start with the molecular reaction. It's okay to still utilize your solubility chart at this point. Be very, very careful. Practice with that solubility chart because you won't have time or the ability to use it on an exam. If you're trying to do this on homework, that's really nice to practice with the solubility chart, but you should start remembering those rules so that they can be brought forward in your mind quickly. All right, potassium +1, chlorine -1 will make KCl. I'm going to go ahead and say I know that that's aqueous because of the potassium. Carbonate and nickel, CO3 minus 2. Nickel here is a +2 charge. I knew that from the subscript of nickel 2 chloride. So I'll make NiCO3. That is a solid. Remember our rule number 6, which said carbonate is usually insoluble except when paired with group 1 lithium, potassium or sodium, or ammonium. Nickel is not one of those, so it's not an exception. So this carbonate compound is insoluble and therefore the precipitate. So we have a reaction, yay! At this point, I want to erase my notes so that I can balance the equation. I see 2 potassiums on the reactant side, 2 chlorines on the reactant side, so I need a 2 in front of potassium chloride. Now, noticing things that are aqueous, these can separate and ionize. In my ionic equation, remember, those subscripts tell you how many are present. There are 2 potassiums. We just did that in the balance, so this shouldn't be something too far off, already fresh in our mind. There are 2 potassium plus 1s for every 1 carbonate. Don't forget, states for each component. Nickel plus 2, aqueous, and 2 chlorides, aqueous. I always tend to run out of room, so it's okay. We'll just go ahead and write this reaction on 2 lines. Typical for an ionic equation. 2 potassium plus 1s and 2 chlorine minus 1s. How did I get that? Don't forget, coefficients get distributed into the entire compound. And finally, nickel to carbonate, solid, no ion there. Now, for my net ionic equation, I do want to identify spectators, potassium and chlorine. So my net ionic equation is written, or my ionic equation is written, but to write the net ionic, I want to remove those spectators. Carbonate, aqueous, plus nickel, aqueous, yields nickel, carbonate, solid. Excellent. The last few sections that we are going to be discussing in this chapter have to deal with other aqueous solutions not containing the dissociation or precipitation of ionic compounds. What we want to be able to discuss is acids and bases, and then we'll see a last type of reaction in an aqueous solution called a redox reaction. So we have a bit of a smorgasbord here for the final sections in this chapter. But overall, what we will see is that all of these reactions are contained in an aqueous solution. So when we start talking about acids, acids have a very simplistic definition in this textbook. There are other types of acids that may not fit into this category of our definition. However, this is the definition we're going to start with. Acids are molecular compounds that form H+ when dissolved in water. Another version of H+ that we have seen in our polyatomic ion discussion is H3O+, or hydronium. So an acid is going to be a compound that when put in water will form H+ ions or react with water to form H3O+ ions. This process, what we see here, is where we require a molecular compound. Notice it is two nonmetals, hydrogen and chlorine. Those two nonmetals form a molecular compound, covalent compound. And when that reacts with water, an H plus ion will get picked up by the water. When H2O gains an H plus, it becomes H3O plus. And that hydronium ion is what is defining that the original HCl covalent compound must have been classified as an acid. Notice what happens is that the Cl minus becomes an anion. So what's happening here is that acids are usually composed of hydrogen. Hydrogen is usually written first in their formulas. 99% of the time we'll see it written first in an acid. And one or more nonmetals is written second. Very typical examples: HCl, H2SO4, HNO3. These are going to be some of our strong acids. Strong meaning reactive acids. We'll talk about those and what they do in just a few minutes. Acetic acid, CH3COOH, is household vinegar. Now, another way to write acetic acid, this is that 1% of the time where this formula, how it's written, the hydrogen that would be the acid is this one. How most textbooks tend to write this, or how I tend to write this, is HC2H3O2, formulating this structure based off of the acetate anion, the polyatomic acetate anion that we saw before. So again, when it reacts with water, we can think of H plus and C2H3O2 minus being the anion that gets removed. So properties of acid: sour taste. Again, that comes from the idea that acetic acid, vinegar, lemon juice also has some citric acid, things like that. Sour tasting. And a lot of their reactivity, they dissolve metals such as zinc and iron, magnesium. They can be used to dissolve pipes, so you want to make sure you don't pour acids down the drain. If you have strong acids, things like that. We see a lot of the depictions over here on the right-hand side. Those bubbles are H2 gas bubbling out of the solution. The acid from any acid dissolving metal will form a reaction where H2 gas usually gets bubbled out. And we'll see that, and why this topic goes well with our redox reactions is because that is also a redox reaction. Not only is it an acid, it also can contribute to an oxidation reduction reaction where gases are formed. Now, where did all of this acid and base definitions come from? It was from this guy right here. His name is Arrhenius. He was Savant Arrhenius was a Swedish scientist. He was originally a physicist, but then he moved to the dark side and found chemistry. He actually received the Nobel Prize in Chemistry in 1903 due to his work on ionic dissociation. Now, Arrhenius is a very interesting backstory. When he was receiving or working on his PhD dissertation, he wrote an actual dissertation that contained 56 theses. He was working on his dissertation in 1884, so a lot earlier than quantum mechanics, right? So we didn't know structures a lot, did not know bonding very well in this time. And Arrhenius put forward 56 theses that are still mostly accepted today with minor modifications. He was a very brilliant chemist who gave us the idea of ions dissociating in a liquid solution. So up until this point, scientists did not fully understand how ionic compounds, when dissolved in water, actually created an electrical current. We saw in the previous sections that dissociation forms when ionic compounds are able to solubilize in water. They form electrolytic solutions, and those electrolytic solutions can conduct electricity. Up until this point, Michael Faraday was the only one who really started to identify ionic compounds in water. And his proposal was that you needed some sort of electrical current to make the ions form. And Arrhenius proposed that even in the absence of the electrical current, aqueous solutions of salts contained ions. And this was his first proposal for that solution reactions are the reactions between ions themselves. Now, his dissertation was not fully accepted at first. A lot of professors at his university thought that it was bogus, or that they, just didn't think that he was correct. So he actually sent his dissertation to a number of scientists throughout Europe. Clausius, who is one of a very renowned chemist in the Clausius-Clapeyron equation in kinetics. He sent it to Van 't Hoff, who we'll see in second semester general chemistry, did a lot of work with physical properties of ionic solutions. And so then finally, it was a way to persuade his dissertation committee and the professors at his university to accept his dissertation and award him his PhD, which I find very ironic, knowing that out of his dissertation, 56 theses are still accepted today. I don't know what people were thinking about back then, that this kid was not brilliant in his own time. Where Arrhenius went with this idea of ionic solutions is the idea that covalent compounds dissolved in water can also produce ions. And this was his idea that a substance that produces H plus when dissolved in water could be a covalent compound, two nonmetals bonded together in a but when they dissolve in water, they ionize. So this proposal, which was incorporated in his PhD thesis, is one of the first acid-base classifications that we learn in general chemistry. Now, again, there are more types of acid-base classifications, but this is the one that we're going to deal with for acids. Acids produce H+. And so any acid that we see should have an H and should have some sort of other nonmetal. And what those do is they separate. H becomes H+1. The other nonmetal gains a -1. So it's this separation of what we call the proton and an anion. Now, why we call that H+1 a proton, remember, hydrogen in its neutral atomic form has one proton and a mass number of 1. That literally means that when he leaves as H+1, he still only has one proton. He just no longer has any electrons. So he gives up his one electron in this reaction. And so the only thing in the nucleus of hydrogen is a proton. And so we normalize it and just call it a proton as a shorthand. Now, there are polyprotic acids, poly meaning many, protic meaning protons. These are acids that contain more than one ionizable proton. And they release them sequentially, meaning they release them one at a time. The best example that we can see is sulfuric acid. H2SO4 can break up into H+1 and HSO4 -1. This would be the first ionization reaction for H2SO4. We don't kick off both of those protons at the same time. The second ionization reaction would be HSO4 -1. It still has one more proton, so we could say it forms H+1 and SO4 -1. 2. So be very careful with polyprotic acids. We'll see them a little bit. Most of our direct use will be with binary acids with just one hydrogen on them. Now, on the other hand, acids always go with bases, substances that produce hydroxide ions in an aqueous solution. Arrhenius's answer to a base was the idea that we had some sort of ionic compound that had hydroxide with it. So sodium hydroxide, lithium hydroxide, potassium hydroxide, calcium hydroxide, any of those ionic compounds that contain the hydroxide polyatomic, OH-1, they would be considered bases. Now again, there are other definitions for bases as well, but this will be our primary definition in this chapter. Here are some common acids and bases that we have to deal with. These could be things that you'll see in the lab or you may see in practice problems. Some of these you'll also just see in household items. Hydrochloric acid has a common name called muriatic acid. If you have a pool or have a jacuzzi, or if you've ever walked through that section of Home Depot, you may see muriatic acid there as a way to clean off calcium and magnesium buildup on your pool. If you have hard water in your area and you have a filter that has a lot of scaling, muriatic acid or hydrochloric acid, HCl, is a very reactive acid in order to clean that off. Hydrobromic acid, hydroiodic acid, those are all other strong acids that are looking very similar to HCl because it's a proton with a halogen. Nitric acid, sulfuric acid, and perchloric acid are all there listed together because these are the strong acids. These are reactive. What does that mean? Is that they are very, very good at donating that first proton. Now, HCl, HBr, HI, nitric acid, and perchloric acid only have one proton to donate. Sulfuric acid is only strong when it has that first ionization step. So be very careful with these. You should know these 6 strong acids. Everything else that has a proton would be considered weak. Acetic acid is a weak acid, meaning that it can release its proton, but it's not very good at doing it. Hydrofluoric acid is also a weak acid. It's not very good at releasing its proton, but it can. I like to bring up hydrofluoric acid here because if you've ever watched Breaking Bad, the show, when it very first started, my husband and I were actually dating at the time, and I very vividly remember sitting down to one of the very first episodes when they pulled hydrofluoric acid out of a high school chemistry lab. I scoffed. I'm sorry. It was a great show, and I applaud them for not teaching people actually how to make meth. But HF would never be found in a high school chemistry lab. 1, it's not a very strong acid, and 2, fluorine is a very weird component in any compound. Because fluorine is such a highly electronegative element, it's a very, very weird, has very, very weird reactivity. And I remember them trying to dissolve a body with hydrofluoric acid, and I remember laughing and saying, that's not how you would dissolve a body. And he married me. We were dating, and we were dating probably a couple weeks when we watched that show together. We stopped watching that show together for sure after that experience. I'm not going to tell you how to dissolve a body, but hopefully after this class, you'll have good enough knowledge to know how to do it later on. Now, for bases, sodium hydroxide is the most common. It's usually what you see in a chemistry laboratory. You might see lithium hydroxide and potassium hydroxide as well. Calcium hydroxide and barium hydroxide are also they're listed under our strong acid categories, or strong bases, strong base category, meaning they are very reactive. You should know these ones as well. What we would want to know about those strong bases is that they give up their hydroxide, they dissociate. Remember, ionic compounds dissociate. The ion OH minus 1 is already there. When you drop it in water, that hydroxide containing salt can solubilize in water. If you go back to our solubility rules of hydroxides, these are the soluble ones. So a strong base is one that is completely soluble, makes a strong electrolyte with water. Ammonia is also written here. Ammonia is not an ionic compound. It is a molecular compound. It is a weak base. So ammonia does not contain hydroxide, but it does produce hydroxide in a reaction with water. But because it's weak, it only does it to a small extent. If we look down at this little reaction at the bottom, NH3, ammonia, reacts with water to produce NH4 plus 1 and hydroxide. There's that hydroxide, OH minus 1. Now, what's important to note is that dynamic equilibrium that we talked about a little bit with our weak electrolytes, meaning that both products and reactants are still present when the reaction is stopped. Not all the ammonia will ionize to form hydroxide. Instead, some ammonia will stay put. It's not reactive enough to just make products. So we have both reactants and products in the solution at the same time. All right, we're going to start with a little bit of naming first. For a binary acid, we're going to start with that type of a naming system. Binary acids have a H plus cation and a non-metal anion. Why we call it these cation anions is simply because we want to start recognizing that H plus in the actual formula. Now, technically, these are not ionic compounds, but they are special covalent compounds that we can treat them as such. So when we think about HCl or HF, these binary acids, an H plus with another non-metal, those are very structured in their naming. Hydro plus the anion with an IC ending followed by acid. So our definition would be hydro plus the anion name with the IC acid ending. So hydrochlorine becomes chloric acid. Hydro and fluorine becomes hydrofluoric acid. The other binary acids that we can see, HBr, hydrobromic acid, and HI, hydroiodic acid. Now, oxy acids are important to note. They are the acids that form from our polyatomic ions. Very interesting endings with these ones. If you recognize that you have a polyatomic ion, what you will notice is that the ending of the polyatomic now changes. Very important. This is not, again, it's not a ionic compound. This is a covalent compound, but it's just a special covalent compound. So the ending of the polyatomic will change. Let's look at these naming a little bit more in depth. We talked about the binary acid, the hydro prefix, and then the ic acid ending. So be very structural with our binary acids. With our oxy acids, we have two different types of endings. If the polyatomic ion name ends in ATE, so nitrate, sulfate, that would become an ending that is ic, IC acid. So NO3 minus 1, when paired with a proton, HNO3, would become nitric acid. If we think about carbonate, CO3 minus 2, you pair that with H plus 1, again, we're treating it like an ionic compound, even though it's not. H2CO3, carbonate becomes carbonic acid. Now, if the polyatomic ends in the ITE, nitrite, sulfite, then the change of the ending is OUS. So sulfite would become sulfurous. Nitrite would become nitrous. So let's write H2SO3. Sulfurous acid, HNO2 nitrous acid. Notice with these oxy acids, we do not have the hydro prefix. The hydro prefix is only for our binary acids. Our polyatomic acids or our oxy acids just get the base name of the polyatomic ion that they contain. Now, an acid-base reaction is also called a neutralization reaction. Why? Well, when an acid reacts with a base, the two neutralize each other. They produce water. An acid donates a proton. The base donates the hydroxide, and we do a double displacement, just like we did before. H and OH make H2O. The anion of the acid and the cation of the base form a salt. So typically what we see as the products of an acid-base reaction is salt and water. Now in an acid-base reaction, as in the precipitation reaction, the reaction occurs when the anion from one reacts with the cation of the other. Now specifically, what's defining our cation of one and our anion of the other is the production of water. So you will see that occur in all acid-base reactions. When an acid and base react, the reaction is called neutralization. So here's an example. We see HNO3, that is the acid, and we see CaOH2, calcium hydroxide, is the base. H and OH come together to make H2O. NO3 and Ca come together to make calcium nitrate. Now, again, we can predict the products the same way that we had done before. And so when we're looking at those products, we can identify their solubility. The salt will either be aqueous or solid. Typically, it's aqueous. Notice here that water is given a liquid. That has to be a liquid because water cannot be in a solution of itself. If water is a solute and the solvent, that's not a solution. That's a pure liquid of water. So water will never have the AQ subscript. It will always have the L subscript when it's in these acid-base reactions for liquid. As long as the salt that forms is soluble in water, the net ionic reaction for a strong acid and a strong base will always be this. This is a good thing to note for a net ionic reaction between strong acid and strong base. And again, we will practice with our ionic reactions soon in class. A neutralization is completed when the moles of the acid are equal to the moles of the base in the solution. This does not always mean the pH is 7. Be very, very careful with that. The pH does not have to equal 7 for a neutralization. Usually for a strong acid reacting with a strong base, when things are completely neutral, yes, that's a pH of 7. But for things when we have weak acids reacting or weak bases reacting, they do not have a neutralization pH of 7. Okay, so we've discussed a lot of the reactivity of acids and bases. Just noting a couple of summary points here. Most chemists interchange H plus and H3O plus. These mean the same thing, and you can call that a proton as well. Just something to note when we're dealing with talking about acids or reading about acids, you can utilize other things outside of your textbook, but just make sure that you're noting the interchangeability of H plus and H3O plus. Bases dissociate in water to form hydroxide ions. Bases such as NH3 don't technically contain hydroxide ions in the actual formula, but when they react with water, they are pulling off the H plus, and therefore OH minus is left over. And then when an acid and base react, it is called a neutralization reaction. We tend to make water and salt as our final products. So here at the molecular level, I want to go through what is happening. Again, when we are looking at an acid-base reaction, HCl, in reality, if it's in an aqueous solution, contains H3O plus and Cl minus ions. NaOH in solution contains Na plus and OH minus. I want to take this reaction and whittle it down from the molecular that we see up here to the ionic and the net ionic. Remember, in an ionic solution or in an ionic reaction, anything that is a strong electrolyte can be dissociated. Nothing else can be dissociated. Our weak electrolytes cannot be dissociated. They would stay just like our precipitates did in their molecular form. So HCl, strong electrolyte. So H plus, aqueous, Cl minus, aqueous. NaOH, strong electrolyte, strong base. Na plus, aqueous, OH minus, aqueous. On our products, NaCl is a strong electrolyte, so it would become the ions. Water is not a strong electrolyte. What we see with water is that it is a liquid and therefore not in a solution, not able to be an electrolyte. So it will not dissociate. I do have some spectator ions, namely Cl minus 1 and Na plus 1. Those spectators I can cancel out for my net ionic reaction. So it just contains the species that actually react, the definition of the acid and the definition of the base to form water. That type of a process will be important, and it should mirror our previous discussions of double displacement reactions. This is a double displacement reaction. It's just now being very specific with what two molecular compounds we're starting off with, or what two compounds in general. Now, acid-base titrations are important for our discussion, just so that we can see the stoichiometry behind these, again, reactions. We would handle these reactions the same way that we previously did with double displacement or precipitation reactions, but a titration usually doesn't focus on the products. A titration is going to be a process in the lab where we have an acid-base reaction, and what we want to find is the actual neutralization point, right? So a question could start off with, you have a specific concentration and volume of acid, how much base at this known concentration is needed to react with the other substance. Or this base, we used 15 milliliters of it, so what's its unknown concentration? So we're mainly in titrations focusing on reactants for our stoichiometry. This is the only difference between precipitation reactions and acid-base neutralizations. In precipitation, we usually focus on how much solid am I getting, how much precipitate do I have at the end of the day. In acid-base titrations, it's how much acid or base do I need so that I don't have an excess or limiting reactant. So we usually don't care about how much water we make or how much salt we make as a product. We focus mainly on the reactants themselves. So how do we do this in the lab? We utilize what we call a burette. A burette is a long test tube looking instrument. It's glass. It's usually calibrated on the side with some graduations or some markings. It's a long glass tube that has very precise volume markings, so that when we think about adding in acid or base, we can find exact volumes of acid or base added. Now, when we add an acid or a base together, how do we know when the endpoint is? How do we know when we've reached the full neutralization? What we want to be able to use is what we call an indicator. Phenolphthalein is the most common indicator. If you've ever watched a CSI or any of those crime scene shows, phenolphthalein is a colored liquid when it reacts with basic things, and it's a clear liquid when it reacts with acids. So it actually is this a big organic looking compound with lots of double bonds in it. We know what a double bond is. So lots of different double bonds, and what we can see is that there's a lot of different resonance structures in this type of compound, so that depending on what type of acidity it's in, whether it's in an acid solution or a basic solution, the color changes. I'll show you a picture in just a few minutes. This chemical is called an indicator. So usually what we do is we put it in either the acid or the base. We put it in the solution at the end of the day, and it changes color at a specific pH. That pH should be around the equivalence point, which means that the number of moles of H plus is equal to the number of moles of OH minus. This would be what we defined as neutralization. So the color change happens at that stoichiometric endpoint, or what we call the equivalence point. We try to get that endpoint and an equivalence point to be almost exactly the same, so that we can be very, very clear on our visualization of when to stop adding acid or base. So in the lab, what this looks like is we have usually a burette, long tube with a little spigot at the end. This is our burette. Usually that contains the base, but it doesn't always have to. Here it does, it contains the base. And down here in our flask is the acid plus the indicator. Now, don't ever forget the indicator. Many a time a chemist has forgotten the indicator and noticed that the reaction keeps going and going, and all they have is a very clear liquid. If you forget the indicator, there won't be a color change, and so you won't know when to stop. So it's very important that you put that indicator in there in the flask. So what we start to do is we start to dribble base into the acid. And what you'll see is that all of these white dots are H plus 1. And when they react with the base, they form H2O. Now, when enough base has entered into the flask to only produce water and have no more left over acid, then we've reached the equivalence point, and we could read the change in volume of base. Knowing that volume of base required, we would know the volume of acid in there, we can start to identify concentrations. Now notice that very, very pale pink. Normally what happens, and I kind of erased it here, you start, when you get very, very close, you start to see these little wisps of pink floating around when the acid has disappeared and the compound, the indicator, is void of acid. What you want to see is a very, very pale baby pink when this phenolphthalein reacts. Phenolphthalein is usually used for strong acids and strong base titrations because it has its equivalence point and its endpoint color change at a pH of 7. Now here is a real life picture of the changes in color. This even would be a little too pink for me on the right-hand side. Maybe a couple extra drops, but in this titration, again, NaOH is added to HCl, and when the NaOH and HCl reach the stoichiometric portions, the equivalence point, the phenolphthalein indicator changes to pink. We will practice with more titrations and stoichiometry in class. Just note that they are very, very similar to our other reactions where we had double displacement, just focusing on something slightly different, being given different starting materials. Last couple things with these. Some reactions are gas evolution reactions. Gases form resulting in bubbling. In both acid-base and gas evolution reactions, as in precipitation, the reaction occurs when an anion from one combines with a cation of the other. So a lot of these are still, again, double displacement reactions. This is just a third category. First category being precipitation, second category being acids and bases. We spend a lot of time with those. Third one, gas evolution. We don't spend too much time here, but they're just really interesting real-life examples. Some reactions form a gas directly from the ion exchange, such as here, when the anion S-2 forms with H+. H2 gas is a gas at room temperature, so that usually bubbles out of the solution. Now I like this next example. When sodium bicarbonate reacts with HCl, what we form is the polyatomic anion HCO3-1 forms with H+1 to yield H2CO3, carbonic acid. Now carbonic acid is a very, very interesting fella because what happens is carbonic acid will automatically form H2O and carbon dioxide. Why this is important to note is because carbon dioxide will bubble out of the solution. Why soda is not good for your teeth? It's actually slightly acidic, not very acidic, just slightly acidic, because we bubble in carbon dioxide, and when carbon dioxide reacts with water, we make carbonic acid. Now the reason why when you open your soda cans, you hear that nice is because the carbon dioxide doesn't like to be in there. So it does bubble out of the solution at normal atmospheric pressure. Remember, when we think about a soda can, we do have to think about that soda can being highly pressurized, usually around 4.4 atm, if we can measure that to keep the carbon dioxide soluble on the shelf. Now, when we open a soda can, the carbon dioxide is just going to bubble out of the solution. The carbonic acid is not very good at staying as carbonic acid. It likes to form water and carbon dioxide. Another example that I have of this reaction, when I was working in industry, I worked for Edison, the electric company. And as a chemist, working with a lot of engineers and mechanics, sometimes I got to use my cool chemistry and solve a problem. One day they noticed a decrease in their pH of a normal basin of water at a peaker plant they had a little bit inland of here in Riverside County. And this basin was supposed to be pure water for a peaker plant. Peakers are very, very efficient, very small generating type stations. They make electricity on a very quick basis, but they're not great to power whole neighborhoods or anything like that. They're just very, very quick at generating some little bit of electricity when something catastrophic happens. So they noticed a little dip in their pH. Normally it should be around 7.2 was normal for them, and it dropped down to about 5.8. And so that's a red flag. You can't put that in a metal contraption that generates electricity because it would corrode, right? Acids corrode metals. And so they knew that. So they called me up and I went down there and we found out that there was actually a carbon dioxide leak in a very, very close container. And it started bubbling carbon dioxide through their water basin. Needless to say, we found the leak and we were able to clean out the water, but it made carbonic acid. And so, yes, some carbonic acid is soluble. It is an aqueous type solution, but because it's a weak acid, remember, it's only weakly ionizing to make H3O+, to make the actual acid form. And so what does tend to happen with H2CO3 is that carbon dioxide will bubble out of the solution instead. This is the best example that we can think of when we're looking at gas evolution reactions. There are a couple listed in your textbook, but I like this one the best just because of the real life example with carbon dioxide. Yes, you can think about soda instead of the power plant. But again, sodium bicarbonate and HCl, if you actually did this reaction, in the double displacement form, you might predict that NaCl is formed, and then you would predict that H2CO3 was formed. That's actually not correct. Instead, you would want to further that reaction and say, instead of H2CO3, I make H2O and carbon dioxide. That would be the correct final set of products for this double displacement reaction. Now you can actually do this reaction if you go to Home Depot and get some muriatic acid and then go to Target and get some baking soda. There you go. You can actually see the carbon dioxide bubble out of the solution. Super exciting. Here are the types of common reactions that undergo gas evolution. So when we make H2S, right? That is straight up a gas, so that would be a state of matter that you would want to know. Carbon dioxide is formed when H2CO3 is a product. Instead of writing H2CO3, you would write H2O plus carbon dioxide. When H2SO3, sulfurous acid, is formed, that again forms H2O and SO2 gas, sulfur dioxide. Don't let that get into your eyeballs. If you remember the reaction earlier, that is the reagent that would float up into your eyeballs and create sulfuric acid. Not good, not good. Ammonia, you would actually write H2O and NH3. So these reactions and these products over here, you would want to be able to write on a given assignment, not the intermediate product written on the left. Okay, our last type of reaction for this chapter is an oxidation reduction reaction, also called redox. Now, in a redox reaction, what's very important to note is that these are reactions that undergo electron transfers. The electrons are transferred from one reactant to the other. Many redox reactions involve a reaction with oxygen. So combustion reactions, very, very typical. Rusting a metal with oxygen, very, very typical for a redox example. H2 and O2 making H2O. I like this example because it's how our hydrogen fuel cells work. It's the simplistic combustion where we don't have a hydrocarbon, we just have hydrogen. And so hydrogen fuel cell cars work on this way, where the things coming out of the exhaust, the tailpipe, is not carbon dioxide like a normal combustion reaction with fuel, like you see C8H18. Instead, it's water vapor, which is incredible to think about. Very, very green chemistry there. So with these redox reactions, combustion is a very typical example. Hydrogen and oxygen react to form gaseous water, right? But is that the only thing? And how can we identify that these are redox reactions or oxidation reduction reactions? To convert a free element into an ion. Now we want to think about the general idea. How do we know a redox reaction occurs? We want to look for the electron transfer. If one electron loses an atom, there must be another element there to accept that electron. We don't have free floating electrons, the actual subatomic particle floating around in a solution. We have ions floating around in the solution. So reactions where electrons are transferred from one atom to another are redox reactions. The atoms that lose the electron are called the oxidation half, or being oxidized. That's referred to oxidation. So things like metals becoming cations, that's a very, very typical example. If the atom gains the electrons, it's being reduced, or it's the reduction part of the reaction. These could be the nonmetals becoming anions. What we see here is this idea that the production of an ionic compound is also another example of a redox. Sodium metal and chlorine gas form sodium chloride. The oxidation half is when sodium becomes sodium +1. That is a loss of electron, and chlorine picks up that electron to become chloride, Cl-1. Identifying redox reactions is tricky unless you use oxidation states. An oxidation state is like a bookkeeping method. Now, these aren't actual charges on the molecules themselves, technically. They're just a bookkeeping to say, where are the electrons around this compound or around this atom? Now, an increase in an oxidation state is oxidation. This is becoming more positive. Losing electrons, right? Losing a negative charge would be becoming more positive. A reduction, on the other hand, is the decrease in oxidation state. This is becoming more negative. There are a lot of acronyms to be able to use. Leo says GER is the most common. Loss of electrons oxidized, gain electrons reduce. Oil rig is also another one. Oxidation is loss. Reduction is gain. Either one of these, what I like about them is the idea that these go hand in hand. Oxidation and reduction have to happen together. You don't just have oxidation by itself. You don't just have reduction by itself. You have to have both. And so when we look at identifying a redox reaction, we are going to be using an oxidation state. Now, what is an oxidation state? It's going to be looking at the general amount of electrons on the reactant and comparing it to that of the product. Notice here, what we are looking at is how carbon changes from a 0 oxidation state to a +4. 0 going to become +4 is becoming positive, becoming more positive. That must mean carbon lost electrons. So it's oxidized. On the other hand, sulfur going from 0 to -2, 0 to -2 is becoming more negative, or reduction, reduced. Now, we need to be able to identify how to determine these oxidation states. So there are rules. It's a hierarchy, so we'll follow the hierarchy. Even though these, again, some of these will be charges, some of them will just look like charges. And so these aren't all ions. For instance, in this previous example, this is not an ionic compound, but we can look at its overall oxidation states based off of the hierarchy and give it some charged idea so that we can formally declare whether the atom gained or lost electrons in that molecular formula. So again, for reactions that are not non-metal to metal or do not involve oxygen, a method of determining how the electrons are transferred is needed. And that method is by assigning oxidation states. All right, so when we want to look at oxidation states, these are, again, bookkeeping. There's a priority here. We start with rule number 1 and we work our way down to rule number 5. Now, there are a couple of categories that have multiple sets, like A's and B's. But overall, what we want to be able to look at is this hierarchy and understand, when given a reaction, can I assign oxidation states and notice a change in oxidation states from reactants to products? The first rule, free elements, sodium, chlorine, oxygen. Anything that you would say is a free element, something that would be an element on the periodic table. Could be a diatomic, but could just be the atom itself. They have an oxidation state of 0. They're in their neutral form. They're by themselves, not bonded to a different atom. Notice how I chose the word different there. A diatomic still is a periodic table free element, even though it's a molecular form. Monoatomic ions, so ions that just have one atom, Na plus 1, Cl minus 1. We could also think about calcium plus 2, or nitrogen minus 3. All of these ions will have an oxidation state that is equal to its charge. So sodium has an oxidation state of plus 1. Chlorine in chloride has an oxidation state of minus 1. Calcium plus 2 is a plus 2 oxidation state, and nitrogen minus 3 is a minus 3 oxidation state. The sum of the oxidation states of all the atoms in a compound will be 0. So for instance, when I look at something like NaCl, I know that that sodium is in an ionic compound that would be plus 1, and that chlorine is a minus 1. So there are their oxidation states. Notice that when we add those up, their overall charge is equal to 0. That's important because when we start to think about the overall charge of things that we may not be predictable, such as in a covalent compound, there are no charges there, but we need to assign an oxidation state, we will be able to use this rule. The sum of all the oxidation states of all the atoms in a compound, in a neutral compound, is going to be 0. Part B with that is the sum of all the oxidation states of an atom in a polyatomic ion is equal to the charge of the ion. In this one, NO3 minus 1, the charges are going to equal, the sum of the oxidation states will be equal to the charge minus 1. Now, when I'm looking at this nitrogen and oxygen, I don't know charges. I don't know oxidation states because this is an overall covalent compound. It's a polyatomic ion that is molecular in nature. So what I'm going to use instead is our hierarchy list. Now we'll get there in a second. What this rule 3b just says is that the sum of our oxidation states will be equal to the charge of the ion. Group 4, for rule number 4 and rule number 5, we're going to use the hierarchy. What starts off with, okay, group 1 metals have an oxidation state of +1 when they're in a compound. So lithium +1, potassium +1, that is understood. Why is it always understood? It's because those are typical. They're very reactive elements in their metallic form. They will always react to form +1 cations. So their oxidation state when they're in an ionic compound is +1. Group 2 metals, again, very reactive, will always have a +2 charge. Beryllium +2, magnesium +2, calcium +2. Right? So when you see group 2 metals having it in their ionic compounds, their oxidation state will always be +2. Now, in a compound, nonmetals will have their oxidation states according to the table over here on the right. Nonmetals higher on the table take priority. So we would always assign fluorine before hydrogen, hydrogen before oxygen, oxygen before the other halogens before sulfur and the rest of the gang in 6A, and that before nitrogen's group in 5A. So when we're looking at these oxidation states, what's important to be able to do is utilize this hierarchy, and we're going to practice just a couple here right now so that we can really truly understand how to use it to assign oxidation states. So let's just grab a couple of examples, and I'm going to keep this set of rules as we start. So KF. Well, it's an ionic compound. I know that because potassium is a metal, fluorine is a nonmetal. I would first look at my hierarchy here and say, well, this has to be +1 for its oxidation state. Now, fluorine comes next on the hierarchy, and I could say, yep, it's typically a -1. Does that make sense? Well, there's no charge up here, right? No charge. So when I sum these up, does that equal 0? Yes, it does. So potassium has an oxidation state of +1. Fluorine has an oxidation state of -1 in potassium fluoride. For a covalent compound such as CO2, it's not as easy. I only can use this chart over here on the right-hand side. I'll start by moving down the hierarchy and I come to oxygen first. So I assign oxygen the -2 oxidation state. Goodness. Now notice that carbon is nowhere on the chart. So what I have to do is I actually have to solve. Whenever we want to find the oxidation state of the last element in my compound, I have to solve for it, utilizing the rule number 3b, the sum of all the 3a or 3b, the sum of all the oxidation states of the atoms in a compound is equal to the overall charge. The overall charge of this covalent compound is 0. So whatever carbon is, I'm going to add it to 2 times -2, and it should equal 0. Now, this 2 is because there's 2 oxygens. All of the atoms, you need to count them up. Each oxygen in CO2 will have an oxidation state of -2. So X minus 4 equals 0. X is equal to +4. So the oxidation state of carbon in CO2 is +4. The oxidation state of oxygen in CO2 is -2. Double check. +4 plus 2 -2s equals 0. Yep, excellent. We'll practice more with this when we get into class. Redox reactions. Again, when we see an oxidation reduction reaction, they must occur simultaneously. So if an atom loses an electron, another atom must take it up. The reactant that reduces an element, the one that is oxidized, remember, if you reduce an element, you are providing an electron. So you, the substance that reduces another element called a reducing agent, are technically oxidized yourself. You are providing the electron for the reduction portion of the reaction. On the other hand, if you are the reactant that oxidizes an element, you are taking away an electron from that element. You are the oxidizing agent, but you yourself are being reduced. So the agent will always be the opposite of what is being happened to that species. So an oxidized element is a reducing agent. A reduced element is the oxidizing agent. So again, an example here. It says sodium is being oxidized while chlorine is being reduced. Sodium is the reducing agent, or sodium is the reducing agent, chlorine is the oxidizing agent. How would we know that? Well, let's just assign oxidation states. What we just learned. Free elements have an oxidation state of 0. So sodium and chlorine, both in the reactants, have an oxidation state of 0. In the products, sodium is a +1 cation. So it's a +1 oxidation state. And chlorine is an anion, a -1 oxidation state. So let's look. Sodium went from sodium 0 to sodium +1. That is oxidation. Chlorine went from 0 to -1. That is gaining an electron, so it's reduction. That's how assigning oxidation states can help us understand what label do we need to put on each of these species. Just a brief note, the transfer of electrons does not need to be a complete transfer, or it doesn't, as it occurs in the formation of the ion. For a reaction to qualify as an oxidation reduction reaction, we need to just see a change of oxidation states. So when we look at some other examples, like this, hydrogen bonds to chlorine, the electrons are unevenly shared, right? And so don't think about these oxidation states as an actual transfer of electrons in this case. They're just a distribution of electrons. Oxidation states, again, are not charges. They are a way of us bookkeeping a distribution of electrons, whether it's an ionic compound or a covalent compound. So again, hydrogen free element, chlorine free element. We would look at HCl and say that it is a covalent compound. So again, using the hierarchy, H comes first, we would assign it a +1. Cl comes after. We would solve if HCl is a neutral covalent compound, their oxidation states have to add up to 0. So that's what we would decide, how we would decide H is +1 and Cl is -1. Again, hydrogen is oxidized because it gets more positive. Chlorine is reduced because it's getting more negative. These are, again, reactions that do not involve combustion. So combustion is not the only thing that we can look at when assigning oxidation states. Your main idea here is to assign oxidation states. That's what we want to be able to do and utilize in a reaction. Now, our last identification in a redox is called the activity series. What this focuses on are our single displacement reactions. We saw double displacement. In single displacement, what we're noticing is that in a typical reaction, we have a solid and an ion, and that electron exchange makes a new solid and a new aqueous ion. Magnesium metal has a tendency to lose electrons, be oxidized, more readily than copper metal. And so when you stick magnesium in copper, copper solution, when you stick magnesium in a copper solution, like what we see up here in this picture, what starts happening is the copper starts plating as a solid on the actual magnesium strip. And what's happening is the magnesium strip is actually crumbling to make magnesium plus 2 ions in the solution. So what's happening is 2 electrons from magnesium are going towards the copper. How do I know there's 2? Magnesium goes from a 0 to a plus 2 oxidation state. Copper goes from a plus 2 to a 0 oxidation state. So that plus 2 exchange literally means 2 electrons are being transferred. Now, if we were to flip and do the second reaction, copper solid in a magnesium ion solution, what we see is no reaction actually occurs. Our theoretical is that maybe we'll get magnesium to plate out and copper ions to form, but in reality, no reaction occurs. And the reason for that is the activity series. It tells us the tendency of reactivity. Now, this reactivity series, I would want you to be able to read. In an activity series table, it lists metals. Now, normally single displacement are metals and metal ions. So our list here is the most reactive, most easily oxidized, the strongest tendency to lose reactions or lose electrons. So lithium, potassium, very, very reactive. If those are our starting solids, these will go forward in creating an aqueous solution. What I want us to think about, go back to that magnesium plus copper solution, put on states. And I just want to note where those 2 half reactions are. I'm going to split up the 2 half reactions. I'm going to take the copper first and say copper plus 2 goes to copper solid. This is a reduction half. Now, that's important to note, is that it's a reduction half because we want to make sure we can identify it on this chart. These on the activity series are oxidation halves, so we have to kind of play with this chart a little bit. But what we could see is that magnesium solid to magnesium plus 2 aqueous is reduction. And so we can find that on the chart. Look at the chart. Oh, excuse me, that is oxidation. Getting more positive, oxidation. Find magnesium on the chart, magnesium right here. And then we'll find copper, copper way down here. Magnesium is better suited to lose electrons, and copper is less likely to lose electrons. What this means is that copper is likely to do the reverse of oxidation, which is reduction. When we want to predict whether a single displacement reaction will happen, we look to this activity series and say, is the oxidation half above the reduction half? If it is, the reaction will happen. If it's not, if the reduction half is written above the oxidation half in our list here, then the reaction doesn't happen. Let's play with one more before we end. Cr, we'll do an expensive one. Chromium reacts with gold solution to produce gold solid and chromium +3 aqueous. Now, what I want to be able to do is write my half reactions so that I can say who is being oxidized, who is being reduced. Well, chromium goes from a 0 oxidation state all the way to a +3 oxidation state. That's oxidized. So Cr going to Cr +3 should be high up on this hierarchy. Gold +3 going to gold solid is reduced because a +3 going to a 0 oxidation state is gaining more electrons. Au +3 yields Au. What we should see is that this half reaction comes first. We want chromium to be more reactive in oxidation than gold. And what we see is yes, it is. This reaction is likely to occur. The reverse, if we were to predict, could we get gold to react in a chromium solution to plate out chromium and to ionize gold? No, most likely not. No reaction here. Because gold is not a reactive reduction agent. It's not good at losing electrons. So gold would not let itself be oxidized. Excellent. This wraps up our discussion of redox reactions. Again, redox reactions being the final form here in our Chapter 8 discussion because of its single displacement nature. The 3 double displacement reactions that we discussed were precipitation, acid-base, and gas evolution reactions.